All right, welcome to Unit 2, Exploring Two Variable Data with AP Statistics. In this video, we are going to cover Topic 2.8, Least Squares Regression. Now, I'm going to warn you, this is a little bit of a longer topic. There are lots of little fine details in here, so there will be two videos for this, Part A and Part B, so you are watching video Part A. All right, since there's so much in this topic, let's kind of give you a little bit of a context or a little bit of a preview of what we're going to learn. So we will explore in more detail the linear regression model that we use to model a linear scatter plot. So in previous videos, we've talked about when you have a scatter plot and you determine that it looks, fairly linear, then what you want to do is use a line or a linear regression model to use to make predictions. And the equation of that line we have seen already is y hat equals a plus bx. But we want to answer questions like, why is this the best line? Like, we call it a line of best fit. Like, that's what you've been calling it probably since 6th grade. But what makes it truly the best line? So we're going to address that. And where do the slope and y-intercept come from? Like, in previous videos, I just gave you the equation for the linear regression model. But where do those values actually come from? We're going to go over that today. And what do the slope and y-intercept mean? Like, they're not just numbers. They actually have meaning in a real-world applicable problem. So we want to make sure we understand that. And then finally, we want to explore how reliable is a regression model at making predictions. If we're going to use a model to try to make predictions, we want to at least make sure we're using a reliable model that we could trust. All right, so let's dive into the first question. Why is the model the best line? Now, to best explain all of these burning questions, we will use the problem that we have been exploring in the last few topics, trucks. All right, so here is that data once again. This is the mileage versus price for Ford F150 supercrew trucks. So we have our table of all of our miles, all of our prices, the explanatory, the response. We have this beautiful scatter plot that looks fairly linear, right? And we definitely can tell that the more miles are on a truck, it would have a tendency to be cheaper in price. All right, so we're going to use this same example a lot this video to explain these new concepts. All right, so first, here is the line that I give you in previous videos. This is the line of best fit. It's called the regression model, right? The linear regression model. It is y hat equals 38,257 minus 0.1629x. But why is this the best line? Like, how come there's not another line that's better? So for example, right on the left here is the best line. And on the right is another line that is clearly not the best. But like, how do I know? How do I know what the best line is? Well, it actually all comes down to residuals. So if I go back to this bigger graph here, if you look at the residuals, you will notice that many of them are negative, many of them are positive, and some are big and some are small. All topics we've covered so far. But every point has a residual. Now, obviously, when we make the line, the best line, we want to minimize all those residuals, right? We want to try to make the residuals as small as possible. Now, nevertheless, we can't keep every point happy. So some points are going to naturally have a little bit larger residuals and some are going to have smaller. But we're trying to keep a nice balance. Now, one thing we could do is add up all of our residuals, right? We could take the sum of all of our residuals. That's the international mathematical symbol for sum. We could take the sum of all of our residuals. Remember, the formula for residual is y actual minus y predicted. And well, the problem is when we do that, we should get zero. Like we addressed that in a previous topic, that when you add up your residuals, you should get something really, really close to zero. If you round a little bit, it might be off a tad, but you should be close to zero. And honestly, mathematicians don't really like using the number zero because you can't really do a whole lot with it. So what they decided to do is they decided to square all of the residuals. So they found all of the residual values for each point and they squared it. So it's literally like they made a square. So instead of just looking at the residual, they made a square of the residual. And basically, you get a bunch of squares. Some are little tiny squares. Some are bigger squares. This one's even bigger. This one's going to be a really big square. And you get the point. Like, this is what it would look like as a picture, literally squaring all the residuals. But realistically, you're just squaring, right? So you got all these residual values and you square them all. And what we want is we want those squares to all be as small as possible, right? So we want the sum of all those squares to be as small as possible, all right? And I know this is a little bit weird to understand, but this I hope is easy to understand. We want the sum of all the residuals to be zero. Just know that mathematicians don't like working with zero too much because there's not really a whole lot you could do with zero. But if we want to think of a number that would tell us that we truly have the best line, it's the sum of all the square residuals. So let me go back to here to make sure you understand why we want this to be small, right? So this is the picture I already had drawn where, again, some residuals were pretty small and some were medium, but overall, none of the residuals were too big. But if you look at this very, very poor line I drew, the residuals are huge. Remember, residuals are vertical distances between an actual point and the line. So even these ones that actually look like they're kind of close are really far away. Like this one right here, like this point right here, it looks pretty close, but when you consider its a vertical distance, it's very, very far away. These ones over here, I even had to extend the blue line just to show all of these points. So if you think about this line, which is a very, very poor line, its square residuals are going to be enormous, right? Even the ones that look small are fairly large. And again, I'm not going to draw all of them here for you, but you can literally see, that looks more like a rectangle, sorry, but you can literally see that when the line is not the best line, the square residuals are huge. Now, this is important to understand because in this blue line that I have drawn, there are positive residuals and there are negative residuals. And like I said, we like that. But just looking at positive and negative doesn't really tell the whole picture. So it's the square residuals that we actually want to be the smallest. And you don't really have to do anything with that. Like I'm never going to ask you to actually square the residuals. But I just want you to understand that's why we call it a least squares regression line. I mean, this is the official formal name of a line of best fit. Like you call it the line of best fit. We kind of then changed it to a linear regression model, and now we're calling it the least squares regression line. The reason why this red line is the best line is because the sum of the square residuals are as small as possible, right? Now you're squaring the numbers. So when you square values, you're going to get positives, and when you add them together, you're going to get a number. Don't get me wrong. But the point is that they're going to be as small as possible. All right, so here is all that in summary. The least squares regression line is truly the best line because it looks to reduce all of the residuals as much as possible. The least squares regression line is the line that minimizes the sum of the square residuals. And here's what that looks like mathematically. The sum of the square residuals. So we use this sigma, big sigma here to represent the mathematical symbol for sum. Y minus y hat is the formula for residual. And then we square all of those residuals. So that's sum is as small as possible. Now, it's never going to be zero. Please, it can't be zero because you're squaring numbers. When you square numbers, A, you're going to get bigger. B, you're going to be positive. And you add them all together, you're only going to be bigger. But the point I'm trying to make is that the sum of the square residuals for the best line is the smallest. And that's the most important thing. All right? You're never going to have to do this. Like, I'm never going to say, hey, I need you to actually find this sum of the square residuals. No, trust me, I will not ask you to do that. But I do want you to understand where it gets this name, least squares regression line. And I do want you to understand why it truly is the best line. Now, one more point I want to make is that every least squares regression line, every line of best fit does go through the point x bar comma y bar. So if you think about the point, the average x and the average y, that point will get crossed on every single line of best fit. That's an important thing to know as well. All right, so hopefully you walk away from this having a, we have to practice this a little bit, but hopefully you have a pretty good understanding of, why we now know it's the best line. It's not just about minimizing residuals, because obviously that we want to do that, but we actually want to make the sum of the square residuals as small as possible. And a line that's not the best line will not do that. So hopefully you have a good understanding of where we get the name least squares regression line. All right, on to the next burning question. Where does this formula come from, right? This is a great formula. Y hat equals A plus BX. Like, it's pretty easy. It's a linear formula. It's a line. Like, it's not that difficult to use. But, where does it actually come from? First and foremost, to find the A, to find the B, you do have to have all of your data points. So that is not a problem, but you just need to know all of your data. Like, you can't find it just by guessing, right? You actually have to know all of your data. All right, now you do have to do it in order. You have to find the slope B first, which I know is kind of frustrating because that's not alphabetical order, but it's just important to know you have to find the slope first. All right, so how do you find the slope? Well, it's a simple formula. It is the correlation R multiplied by the standard deviation of all the y values divided by the standard deviation of all the x values. So it's a pretty simple formula, but to know the standard deviation of the y's, you gotta do the math. To know the standard deviation of all the x values, you gotta do the math. All right, and then we move on to finding the y-intercept. The y-intercept must be found after the slope, and you'll see why in 1 second. And it involves another fairly simple formula. To find the y-intercept A, you take the average of all the y's minus the slope, hence why you have to find slope first, times the average of all the x's. Now, how do you get the average y? Well, you got to know the data and you got to be able to calculate it. How do you find the average x? Well, you got to know the data and you got to be able to calculate it. So these are the two formulas that produce the A and the B. These numbers are coefficients, right? Coefficients are numbers in front of variables. So once you solve to find B and A, you will know the coefficients. Please keep in mind that x and y are variables. They represent something. X represents, in our example, the miles of a truck, where y represents the price of the truck. A and B are coefficients because once you use the formulas, you're going to get numbers. All right, so let's make sure you understand how to use these two formulas. All right, here is our data on the Ford F150s, and I went ahead for you. At the bottom of this chart, I went ahead and found the mean of all of the miles. I found the mean of all the prices, and I also found the standard deviations of each, and I found the correlation. Now, how did I do all that? Well, to be honest, I used Google Sheets because Google Sheets is a nice way to find all that for you. You could also use your calculator, TI-84. You could get a list of data and find the mean, find the standard deviation. We went all over that in Unit 1. We'll cover it again in class, but that is how I came up with this data. And remember, typically the correlation will always be given to you. You're not going to have to find that. It'll be given to you. But again, technology, computers, and calculators can find it for you. All right, so once you have all that information, all you got to do is, well, use it. So remember, you got to find slope first. Slope takes R, negative 0.8150. It multiplies it by the standard deviation of y. So that's important, right? You can't mess this up. So make sure you remember from your scatter plot that x is the miles, and that explains the price y. So the standard deviation of y and x, make sure you keep these straight. The standard deviation of y is 9570.42, all divided by the standard deviation of x, which is miles, 47876.83. All right, so lots of numbers there. Keep things in order. The number one thing I've noticed that kids mess up on the past is they flip-flop the x's and y's. So be very careful to take your time and make sure that the standard deviation is going on top for y, standard deviation for x on the bottom. The other thing that a lot of kids do is they accidentally use the means in this formula because they just look at the chart, they get a little confused, and they don't stop and think. So make sure you are looking at the row for standard deviation. All right, so I'm going to go ahead and use my calculator here. If you want to go with me, you can use your calculator, but I mean, come on guys, it's pretty simple math. Take the negative 0.8150 times 9570.42 and divide that by 47876.83, and you get negative 0.1629. Negative 0.1629. And if you remember from previous topics, that is the slope that we were using. I just never told you where it came from. All right, now we're going to go ahead and find the y-intercept A. To do this, we take the average y. The average price of a truck was $27,833.69 minus, now we got to take the slope we just found, negative 0.1629, and multiply that by the average of the x's, which is the average number of miles, which is 63,979.50. All right, so be careful. That is going to turn into a plus sign because when you subtract a negative, it does make a positive. So I'm going to go ahead and type this in, 27833.69 minus negative 0.1629 times 63979.50. And I get 38,000. let me see here. Sorry, 38,255.95. 255.95. All right, now, I do want to tell you something real quick. Let's go back all the way up to where I first introduced the truck problem. And notice the equation right here, right? The equation did have the slope of 0.1629, as I just solved for. And then it has the y-intercept of 38,257. Now, that is a little bit different than what I got, but not by much. I mean, just barely, right? I mean, off by a little bit. I got 38,250. Technically, if you would round that up, it'd be 38,256. So I'm really close. Now, why? Well, this is rounded a little bit. I rounded the average y, and then I rounded the average x, right? Those were just rounded to 2 decimals. And then even the slope was rounded a little bit. So you combine all that rounding, and you might not get the exact value, but it should be pretty close. I mean, if this is a test or quiz, I'm not going to mark that wrong because you are so close. It's just a little bit of rounding. So at the end of the day, based on my calculations, the regression model equation is 38,255.95 minus 0.1629 times x. Very, very nice way. All right, now, the other thing I do want to tell you is that most of the time, no one's going to make you do all this work, right? And to be honest, if I am going to make you do all this work, I'm going to give you a table just like this. Like, I'm not going to expect you to take all of your data, find the mean, find the standard deviation, do it for the x's, do it for the y's, find the correlation. If I want you to utilize this formula for B and A, I'm going to give you everything you need. I just want to make sure you know how to use the formula, right? So that's pretty much it, right? So in a nutshell, how do you get the linear model? Well, there's actually 3 ways you can get the linear model. 1, you could use all the data like we just did to get R, get the means for X and Y, get the standard deviations for X and Y, and then use the formulas to find slope and find y-intercept. That is what's going to happen. But again, very rarely will I honestly make you do that. And if I do make you do that, I will give you all the data you need. You just have to know how to plug it into the formula. And a second way that you could get the linear model is that, honestly, I just straight up give it to you for free. And I'll be honest, typically the AP Stats does that. Like, they don't want a kid to make a silly math mistake and get a whole problem wrong. So they would rather just give you the equation and have you focus on using it than finding it. That is something that's very, very typical. So expect on a lot of problems for me to just give you the equation free of charge. And then the third way that I can give you the linear regression model is with what's called a computer regression output. Now, this is a little bit confusing to understand, but I hope that I'll do a decent job of it. So imagine that you have a computer, maybe Excel or Google Sheets, or even your calculator, and you plug all of the data into your calculator, and you're going to ask the calculator or computer to do all the work for you, because, you know, that's what computers do. They do math work for you. So it's going to take all that data, and if it's going to do everything for you, it needs to spit it out in a way that you can read it and understand it. And it does so with a computer output table. So imagine a computer, and you feed in all the data, all the x's, all the y's, and it gives you an output that you could read to understand what everything is. And this right here at the bottom is an example of a computer output table. So first off, right now, we do not need p-value, we do not need t-value, we do not need standard error. Those will come back at the very, very end of the year, way back in Unit 9, but not right now. The main things we need are the coefficients, right? The coefficients are the slope and the y-intercept. That's what we need. And they are perfectly here. You'll see the word intercept, and right next to the word intercept is the A value. That is your y-intercept. And then right below that is the slope. That is your B value. So it actually does go in alphabetical order, A on top and then B. And it actually labels the intercept for you. It says intercept, so you can't really mess that up. Now, unfortunately, it doesn't say slope right here. What it does is it gives you the X value, right? So when you're reading one of these computer output tables, that is the X value. So that tells you that miles is the X value. But realistically, all you need to know is that in the column for coefficients are the 2 numbers you need, A and B. And the nice thing about a computer output table is a computer doesn't do any rounding. So these numbers are as exact as possible. Now, when you actually go ahead and write out the equation, you do not need all those decimals. I would probably just do 38,257.13, or actually it should be 0.14, minus 0.1629 times x. Okay, so, keep 2 to 4 decimals. I'm going to be honest. I like 4 decimals, but a lot of people keep 2. But you don't have to write all of them. But a computer output table typically will give you a lot of them just because it can. So again, don't ever worry about these other columns. We're not going to use those right now. We're looking at theirs. So, let's just review this, right? One way that you could find the model is do all the work. Second way is I just give it to you, like free of charge. Awesome. Third way is that you actually have to get dirty and look at one of these computer output tables, which, to be honest, is essentially just me giving you the equation. All you have to know is how to look for the slope and the y-intercept, A and B. So pretty easy. You don't have to really do any work. It's just a nice way that we could give you everything you need. Now, the other numbers in this table, R squared and S, we are going to learn in part 2 of this topic. So that's it for part 1. We learned why it's called a least squares regression line and why it truly is the best line. And we learned how to get the equation, how to get the linear regression model that we so covet. And in the next video, we're going to talk a little bit about reliability. All right, guys, see you in video part B.